universe is part of something larger. The scale of the Earth and its moon may be relatively easy for the human mind to grasp, but the nearest star is unimaginably remote, and the farthest galaxies are billions of times more distant yet. Cosmologists who study the size and structure of the universe use mathematical models to build a picture of the universe's vast scale. Cosmologists may never determine exactly how big the universe is. It could be infinite. Alternately, it might have a finite volume. But even a finite universe would have no centre or boundaries and would curve in on itself. So paradoxically, an object travelling off in one direction would eventually reappear from the opposite direction. What is certain is that the universe is expanding and has been doing so ever since its origins in the Big Bang 13.7 billion years ago. By studying the patterns of radiation left from the Big Bang, cosmologists can estimate the minimum size of the universe. Should it turn out to be finite, some parts may be separated by at least tens of billions of light years, as a light year is the distance that light travels in a year, 9,460 billion kilometres. The universe is bewilderingly big. Although the universe has no edges and may be infinite, the part of it that scientists have knowledge of is bounded and finite, called the observable universe. It is a spherical region around the Earth from which light has had time to reach us since the universe began. The boundary that separates this region from the rest of the universe is called the cosmic light horizon. Light reaching Earth from an object very close to this horizon must have been travelling for most of the age of the universe, that is approximately 13.7 billion years. This light must have travelled a distance of around 13.7 billion light years to reach Earth. Such a distance can be defined as a look back or light travel time distance between Earth and the distant object. However, the true distance is much greater, because since the light arriving at Earth left the object has been carried further away by the universe's expansion. So that's the introduction to the scale of the universe. Then move on to celestial objects. The universe consists of energy, space, and matter. Some of the matter drifts through space as single atoms or simple gas molecules. Other matter clumps into islands of material, from dust motes to giant suns, or implodes to form black holes. Gravity binds all of these objects together into great clouds and disks of materials known as galaxies. Galaxies in turn fall into clusters and finally form the biggest celestial objects of all, superclusters. Much of the ordinary matter in the universe exists as a thin and tenuous gas within and around galaxies, and as even thinner gas between galaxies. The gas is made mainly of hydrogen and helium atoms, but some clouds inside galaxies contain atoms of heavier chemical elements and simple molecules. Mixed in with the galactic gas clouds is dust, tiny solid particles of carbon and substances such as silicates. from stars and re-radiate it as light. In contrast, dark nebulae are visible only as smudges that block out other starlight. Particles of matter also exist in space in the form of cosmic rays, highly energetic subatomic particles travelling at high speed through the cosmos. Stars and brown dwarfs. The universe's light comes mainly from stars, hot balls of gas that generate energy through nuclear fusion in their cores. Stars form from the condensation of clumps of gas and dust in nebulae and sometimes occur in parts, pairs or clusters. Depending on their initial mass, stars vary in colour, surface temperature, brightness and lifespan. The most massive stars, known as giants and supergiants, are the hottest and brightest, but last only for a few million years. Low-mass stars, the most numerous, are small, dim, red, and many live for billions of years. They are called red dwarfs. Smaller yet are brown dwarfs. These are failed stars, not massive or hot enough to sustain the type of fusion that occurs in stars and emit only dim glow. Brown dwarfs may account for a lot of the ordinary matter in the universe. Star remnants. Stars do not last forever. Even the smallest, longest-lived red dwarfs eventually fade away. Stars of medium mass, such as our Sun, expand into large, low-density stars, called red giants, before they blow off most of their outer layers. They then collapse to form white dwarf stars that gradually cool and fade. The expanding shells of blown-off matter surrounding such stars are called planetary nebulae, although they have nothing to do with the planets. More massive stars have yet more spectacular ends, disintegrating in explosions called supernovae. The expanding shell of ejected matter may be seen for thousands of years and is called a supernova remnant. Not all the star's material is blown off, however. Part of the core collapses to a compact, extremely dense object called a neutron star. The most massive stars of all collapse into black holes. Planets and smaller bodies. The solar system, our own star the Sun, and everything that orbits it, is thought to have formed from dust and gas that condensed into a spinning disk called a protoplanetary disk. The central material became the Sun, whilst the outer matter formed planets and other small cold objects. A planet is a sphere orbiting a star, and unlike brown dwarfs, producing no nuclear fusion. As planets and protoplanetary disks are found orbiting stars elsewhere in our galaxy, it is probable that the solar system is typical and that planets are common in the universe. In the solar system, the planets are either gas giants such as Jupiter, or smaller rocky bodies such as Earth and Mars. Yet smaller objects fall into several categories. Moons are objects that orbit planets or asteroids. Asteroids are rocky bodies from about 50 miles to 1,000 kilometers. Comets are to form atoms and ions. In addition to these well understood types of matter, other forms exist. Most of the universe's matter consists of this dark matter, whose exact nature is still unknown. What is matter? Matter is anything that possesses mass, that is, anything affected by gravity. Most matter on Earth is made of atoms and ions. Elsewhere in the universe, however, matter exists under a vast range of conditions and takes a variety of forms, from thin interstellar medium to the matter in infinitely dense black holes. Not all of this matter is made of atoms, but all matter is made of some kind of particle. Certain types of particle are fundamental, that is, they are not made of smaller subunits. The most common particles within ordinary matter are quarks and electrons, which make up atoms and ions that form all visible matter. Most of the universe's matter, however, is not ordinary matter, but dark matter, perhaps composed partly of neutrinos, theoretical WIMPs, weak interacting massive particles, or both. Atoms are composed of fundamental particles called quarks and electrons. The quarks are bound in groups of 3 by gluons, which are massless particles of force. The quark group forms particles called protons and neutrons. These are clustered in a compact region of the centre of the atom called the nucleus. Most of the rest of the atom is empty space, but moving around within this space are electrons. These carry a negative electrical charge and have a very low mass. Nearly all the mass in an atom is in the protons and neutrons. Atoms always contain equal numbers of protons, positively charged, and electrons, negatively charged, and so are electrically neutral. If they lose or gain electrons, they become charged particles called ions. Chemical elements. Atoms are not all the same. They can hold different numbers of protons, neutrons, and electrons. A substance made of atoms of just one type is called a chemical element, and is given an atomic number equal to the number of protons and thus electrons in its atoms. Examples are hydrogen, with an atomic number of 1. All hydrogen atoms contain 1 proton and 1 electron. Helium, atomic number of 2, and carbon, number 6. Altogether, there are 90 naturally occurring elements. The atoms of any element are all the same size, and crucially contain the same configuration of electrons, which is unique to that element and gives it a specific chemical properties. The universe once consisted almost entirely covalent compounds such as water, the atoms are held in structures called molecules by the sharing of electrons between them. Two or more identical atoms can also combine to form molecules of certain elements. The book then moves into states of matter, forces inside of matter, particle physics, nuclear fusion and fission. This is just all the basics of the start of the book. I missed out the very first few pages, which was the general introduction to the book and the universe, with the first introduction type of various pictures and visual guides. All the parts after that I have been reading are the introduction to the basic fundamentals that the book then uses to cover different subjects. Later on it moves on to specifics such as planets, life in the universe, looking for life, forces, astronomy, and there's a lot more photos, pictures and detailed descriptions, graphs. It's very visually interactive, and as it is a large book, the artwork and the pictures have been very well done. That's all I'm going to try and read for now, because I just wanted to see how a reading would come across. And for some reason it feels like it takes a bit more concentration from myself than if I was reading quietly to myself. Maybe it's because I'm concentrating because I'm actually holding the microphone in my hand rather than on a stand of some sort. The book's just awkward to fit on the table with the microphone as well. But if anyone likes the reading, thinks it might be a good thing to get a few more videos of, as I know I do like some of the reading videos that people do. Pure reading, just because I prefer listening to those type of ASMR videos when trying to sleep, as I don't have to actually watch the video. I can just put it on and listen and not really care about what's being read, although I have been interested by some of the readings I've actually listened to. And as this is quite a full-on subject, I suppose, even though it's just the basics, I'm quite sure me reading it can probably be quite tedious and boring. So it might be quite good for getting people to relax and to sleep. We shall see. I hope everyone will have to let me know what they think. And if they come across well, I will certainly do some more, because it can be quite relaxing. It's unusual to be reading aloud, to be honest. But it's quite relaxing to do myself. I'd like to say thanks to everyone, all the few new subscribers I've had as well. Again, much appreciated. And I hope I can get a few more videos up. I've finished for the week, so I'm going to try and get this video up, and I'm going to do another one tomorrow, I hope. I'm not sure what of yet though. I may do another reading, I may try something else. Just want to get a range of things up so I can see what people prefer, what works best, what sounds best. But I hope the microphone, and I'm getting better at the settings at